This second part of Bayesian arithmetics, we're going to talk about sign binary representation. Those are typically used in computing whenever positive and negative integer must be processed, stored, or calculated. They're often used in computer arithmetics, programming data types, in C, Java, when you want to do byte charts long, sensor data and signal processing as well, and embedded systems. The key difference from unsigned is that you have a signed bit, and you think about the most significant bit that is going to act as a signed bit, being a 0 for positive or 1 for negative. The range is usually an 8-bit unsigned number that represents number from 0 to 255, and a signed 8-bit number usually goes from minus 128 to 127. So let's take a look at how that works. So the unsigned binary number can only represent numbers from 0, 1 up to 2 to the n minus 1, but we need a convention for negatives. So the idea is that we pick the MSB, or the most significant bit, as a signed bit, with 0 for positive and 1 for negative. So for example, here for 5, you have the most significant bit here being 0 because this is positive, and in here you have it as 1 because it's negative. Here, this is an 8-bit representation. Now, the problem with the sign magnitude is that we have two representations of 0. Then we're going to have 0, 0, 0 for positive 0, and 1, 0, 0, 0, 0 for minus 0 or negative 0. The arithmetics is going to be complicated because addition and subtraction is going to be handled as separate cases, so that might overcomplicate things. Better alternatives are going to be complement representation that are going to eliminate this problem by making the arithmetics uniform. So the one complement rule is the initial step, and what we do is to negate a number, we flip every bit, we transform zeros and 1, and the most significant bit is still going to be this sign bit. So for example here, we'll start with plus 5, that is going to have a value, of course, of plus 5. The 8-bit pattern representation of that is going to be 0, 0, 0, 0, 0, 1, 0, 1. Notice that this is still on binary representation, so this is what you can see, that we have a 2 on 2 to the 2 position, and a 1 in the 2 to the 0 position. So this is going to add up to 5 if we transform this to decimal. Now, if we want to represent that plus 5 in the one complement rule, this minus 5 is going to flip all the bits. So now everything that it was a 0 before now is going to be a 1, and everything that is 1 before is going to be a 0. So notice that now it's 1, 1, 1, 1, 0, 1, 0. Now, for a number like plus 17, then you will have that this is 0, 0, 0, 1, 0, 0, 0, 0, 1, and flip into minus 17, that will give me 1, 1, 1, 0, 1, 1, 1, 0. The problem is that we'll still have 0 showing up as an issue with two representations. Plus 0 is still 0, 0, 0, 0, but minus 0 is just going to be 8 bits of 1. So it also have a range problem because for the n bit 1 complement, we're going to flip from minus 2n to the minus 1 minus 1 to plus 2n minus 1 minus 1. So essentially we're going from minus 127 to 127 in the example of the 8 bits. So what we do instead, and is the most common system that is used, is the 2 complement rule, which is to negate, we flip every bit, then we're going to add 1 to the result. So equivalently, we're going to flip all the bits to the left to the rightmost one. So let's see a 8-bit example finding the representation for minus 5. So we'll start once again with 5, the representation in 8-bit of 5. Then we flip all the bits to the complement, which is going to be ones. So we have 1, 1, 1, 1, 1, 1, 0, 1, 0. Then we're going to add 1. And so we're going to be adding this here 1 representation, which is 0, 0, 0, 0, 1. And then once that we add that, then notice that we're just going to have the representation 1, 1, 1, 1, 1, 0, 1, 1. This is going to be minus 5 in 2 complement rule. Now, the good thing about the 2 complement rule is that 0 has a unique representation. 0 is just 0, 0, 0. You don't have minus 0 being different. So it's good because of that. The range is a little bit better. We go from minus 2 to the n minus 1 to 2 to the n minus 1 minus 1. So essentially in 8 bits, we're going from the number minus 128 to plus 127. We are flipping all the bits, and the most significant bit is going to be the 1. And we get to add 1 to get the magnitude. Now, we can also see the 4-bit to complement values. So here we're going to have a range from minus 8 to plus 7, just to give an example. And so this is the representation given by this table. You can pretty much find out what is the value in decimal base by just putting this in terms of what the powers of this are going to be. Now, the most significant bit here will be 0, that will be positive, and the most significant bit being 1 means that it's negative. Note that there is an asymmetry here, and we have one extra negative value, and minus 2n to the minus 1 has no positive counterpart. So we have minus 8, but we don't have 8. Okay? Now, the big win of this is that for arithmetics, is going to be very good. We're just going to add normally and discard any carryouts of the most significant bit. So we're not going to change it. But we have no special cases for negative numbers. So for example, if we're going to add plus 7 plus minus 3, which will give me plus 4 in 8 bits, then that will be the representation of 7, which will be 0, 0, 0, 0, 0, 1, 1, 1. And then we're going to add the representation of minus 3, which once again will be 0, 0, 0, 0, 0, 0, 1, 1. But we flip it and we add 1, so we get this number. Notice that we will have all the zeros becoming 1 here. This 1 becomes a 0. This 1 becomes a 0, but because we add 1, then we get this 1. So now we have the representation, and then we can add just those numbers and add normally. So 1 with 1 is 0, I carry 1. 1 plus 1 is 0, I carry 1. 1 plus 1 is 0, plus 1 is 1, I carry 1. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. 1 plus 1 0, carry 1. 1 plus 1 0, but I discard the last change because we're not going to use anything for the most significant bit. So we carry out here, and we notice that we're going to get the representation for 4, which is given by this positioning. Another example of this will be, let's do minus 5 plus 3, which is going to give me minus 2. When you have the representation for minus 5, once again, you can start with the representation for 5, which is going to be 2 to the 2. So 1 in the position number 2 and 1 in the position of 1. And then you can flip that and add 1. So we're going to get this number 1, 1, 1, 1, 1, 0, 1, 1. And then we're going to add it just with 3. And so once again, the representation is given, then you can do the operation. 1 plus 1 is 0, carry 1. 1 plus 1 is 0 plus 1, 1, carry 1. Then we get this 1 here. 1 plus 0 is 1. 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 And we don't need to cancel anything out since we're not doing any carries. Now, we decode this. We flip it around just to know what number this is going to be. And so notice that this is just the 0, 0, 0, 0, 0, 0, 1 plus 1 at the end. So this is just going to be the number 2. So because of the rule, then this number will be equivalent to minus 2. Notice that we go back to the original representation to be able to understand what number this is. And then we flip the sign so we can know what this is on the um, on the sign representation. Okay, so one key definition here is going to be the overflow, which that occurs when the true mathematical result cannot be represented in n bits. The most significant bit, sign bit, is going to be corrupted. The overflow rule happens if and only if both operands have the same sign and the result has the opposite sign. So, for example, here we have 120 plus 100 plus 10, really. So we are doing two positives, but then when we add, we're going to have a negative bit here. And so the true result here is 130, which is going to be bigger than 127, which is an overflow. Now, when we have positive here, positive 5 plus negative 3, we didn't have overflow. We have mixed signs, so mixed signs never overflow. So you got to pay attention with overflows when you have two positives. Okay, in summary for this section, we learned Bayesian notation, how the digit representation works. We learned about binary, octal, and hexadecimal, the binary arithmetics that we can do with all those numbers and base 2. We also learn about signs bits representation, the one complement, two complement rule, and possible when we have overflow. Okay. So important things not to mistake is using the wrong base, being careful with the most significant and the least significant bits, grouping bits on the wrong direction when we're doing pattern to the left. Grouping to the left might give you the wrong octal hex digit representation. When you're doing sign transformation, you gotta be careful when you're doing one complement versus two complement, because in one complement you only flip the bits, and two complement you flip the bits and then you're adding one. They're gonna differ exactly by one for every negative value. Last, you gotta be careful not to forget to discard the carryouts on the two complement addition. A carryout of the most significant bit is normal and needs to be dropped. It is not overflow. Overflow is detected by sign, not by carry. Okay, so this is the end of the chapter on Bayesian arithmetics and the end of the content for discrete mathematics.